Hello, welcome back. We are in our third lesson. We are studying of Unit 2. We are studying linked lists. I'd like to start by reviewing the big O notation for the runtime complexity of a singly linked list. Then we'll discuss some changes that we're going to make. All right, first of all, linked list. What is it? I've got a little picture of it here to help you think about it, okay? And remember that we have a reference to first right here, which I'll just call F, and first is referencing that node. And then to access the sequential nodes, we have to use the next reference within each node. So what does it take to insert the front? Well, since you've got a reference to the front, we can insert the front in constant time, O1. It's just a couple of steps. There's no looping, there's no iterating, there's nothing. We can also remove from the front very easily, also at O1. And we can view the front. And when I say view, I mean access it, get it, set it, whatever you want to do. I'm just saying view to include all those operations, O1 as well. And that was the chief advantage of our singly linked list. It allows us to access in constant time the front of the list. Whereas with the array list, you'll recall that removing or inserting at the front were extremely slow, O(n). Now, viewing, though, was O1 for an array list. Which is, when I say array list, I mean a list backed by an expandable array. All right, what about inserting at the back, though? Well, in order to do that, I have to start at the front and then go to the second node, the third node, the fourth node, all the way through every single item in the data. So that would be O(n), because I have to loop through all in data. And that means it's also going to be that to remove from the back and view the back. So that's terribly slow. So it's kind of the reverse of the array list. What about inserting? Now, when I say that, just insert, I mean insert anywhere, right? So on average, inserting anywhere, I have to iterate through everything. So that's O(n). You know, even if it's on average really O(n) divided by 2, so I'll probably on average only have to iterate through half the nodes, we still call that O(n), which means that removing it is also O(n), and viewing it is also O(n). Now, just to compare that to array list, with array list though, inserting in the middle, removing in the middle, that was also O(n). But remember, we could access, which means set or get, any index in array list in constant time. So that's where we're really losing out right here, is with the viewing of the back and viewing at the specific index being O(n). That's the shortcoming for our linked list. But today what I'd like to do is I'd like to improve greatly on this, okay? Because we can make this not be O(n) in this whole thing. So we're gonna develop a different kind of linked list that is going to allow us to have constant time to access, view, remove, or add to the back. So without further ado, let's create a class called Doubly linked list. So, and we're going to use integers today because it's just going to be easy for us. So public class Doubly linked. And let's just get this started up. Just so you know, have a project. I'm in my linked list project. Now let's go ahead and discuss what's going to be in that class. So I've got a diagram here of a doubly linked list. So earlier we kept a reference to first. Well, we're just going to add one more reference. We're going to keep a reference to last. So by having a reference to first and to last, that's going to really help us because we can now immediately access the first or the last element in our list. But in order to do so effectively and to make this last at all useful, we need to have references going the other direction as well. So from now on, we're going to be making our nodes have two references. They'll have a reference to the next node that comes after it in the indices, and we'll have a reference to the previous node that comes before it. So we're now going to have both next and previous. So in the first node, previous is going to point to null because there is no node before the first node. And next will point to null because there is no node after the last one. And we are going to have to deal with some special cases when we have an empty list or our first and last are the same thing, meaning that we only have one element in our list. So we'll keep a lookout for those kind of things. So let's go ahead and make our node class. I think you can see what our node class is to have. We're going to be using int data, node next, node previous. So pause the video and please make your nested node class. Okay, here we go. I'll make it a private class node, and it's going to have int data, because we're using ints just to keep things simple. We could just as easily use our generics right here, or any other type that we want. And we'll use a reference to the next node, and we'll keep a reference to the previous node. Upon creation of a node, I would like to set the data to what the user gives me. Okay. Next, I'm going to set to null, and previous to null as well. Now, these values would have been set for us automatically by Java, because if you don't set the value of an instance variable, it gets a default value of null for object types, for reference types, that is. But I like to be explicit. All right, so we've got that taken care of. We've made our node for the doubly linked list, but we do need to go ahead and make these references to first and last. So we need to make a couple of fields here that we are instance variables. I'm trying to use that vocabulary now. Private node first, private node last, and of course we want to keep a reference to the size. We want to keep track of that. Let's make our constructor. And first will be null when we start, last will be null, and size would be 0. And of course, those are all the default values, but like I always say, I want to be explicit. I like my code to show exactly how I'm going to have things start. All right, let's get to our first operation. First thing we're going to do is we're going to add to the front. We've already added to the front of a list. This one's going to be just slightly more complicated because of the doubly linked nature. So let's say we have a list of just these 3 nodes here, okay? And I have a reference to the first and the last. I'm now going to add a new node, which I'm going to show here on this next little slide. So, oops, too far. So first thing I'm going to do is I'm going to make some new node, maybe call this temp or something like that. So we're going to make a new node, and it's going to store the variable, the data value that our users are wanting us to store. And I need to connect next to the first node, because it's going to be the first node, so I need to connect it to first, which will then be the second node. Likewise, I need to connect previous to this node. So I want to connect the first, I want to connect my temporary nodes next to first, and I want to connect first previous to my new node. Then, after that, I simply move first to my new node, that reference, and everything's going to be just fine. However, there is a couple of, there's a nuance here. We need to deal with the fact that what if you have an empty list? Well, if we have an empty list, whatever node we make needs to be both the first and the last node. Make sense? So just, you need to check that first. And we can do that by saying if size equals 0 or if first equals null, and that would be fine. Okay, what I'd like you to do is I'd like you to pause the video, and then I want you to write the code add to front. Okay? So add to front that takes in an int data and adds it. Please make sure that you're doing your absolute best to do this. If you wait and just look at how I code it, you're really not going to learn. Even if you don't get it right, you have to give it your best shot. Look again at the information, see what's happening. The key slide here is this one here that shows you do that next first, then you do first previous, and then you finally transfer first over. You got to do it in the right order. All right, give it a shot. All right, let's see how we did. We called it add the front, right? All right, first thing I'm going to do is I'm going to make that, I'm going to make a new node. So node temp equals new node with the data. Now, if first is equal to null, so that means that size is 0, then I am going to say first gets assigned to temp, and last gets assigned to temp, and that's it. Otherwise, we're going to do something else. All right. And before I go any further, I am going to go ahead and write size plus plus since we're adding every time. I don't want to forget that. That causes all sorts of issues later, right? So otherwise, we're in our more general situation where the list is not empty. We've already got a temp node made, so let's start connecting. I'm going to say temp.next is going to be assigned the reference of first, and first.previous will be assigned the temp, and then finally, first is going to be connected to temp, and that is all. Okay, let's go on to our next operation. Our next operation that I want to do is let's try add to back. So public void add to back. Give it a try. See if you can figure out how to do it. Don't think I have I don't have an image for that, but if you think about it, it is really the same as adding to the front my image here. You just need to consider doing it at the back and how that would work. So think about what it would look like to add a new node over here. So, we're going to be shoestringing the previous. This next is going to go here. Okay, and then last, we'll move the last reference. So give it a try. And don't forget the special case of when the list is empty. All right, once again, and I could do this later, but I'm going to go ahead and do it. Two things first. I'm going to make size go up so I don't forget to do that. And I'll just code on top of that. I'm going to make a temporary node like that. And, if first is equal to null, or in other words, if size equals 0, I can do that as well. Then I'm going to say first is equal to temp, and last is temp as well. So we're assigning the reference of first to point at the temporary node I just made, and last will also point at that node. And I don't have to connect next or previous to anything because there is no next, there is no previous. All right, else, what are we going to do elsewise? Well, we need to take my temporary node's previous. Right now, temporary's next is connected to null, and its previous is connected to null. We want to keep its next connected to null because it's going to be at the back, so there is no next. But its previous reference, I want that previous reference set to reference the last. And I want last currently is got a no next because it was the last element, but it's not the last anymore. I want next to point to temp. And then finally, I'm going to change that last is now not going to reference what is now going to reference temp, and what used to be last will now be second to last. And we've got our size increase, so we are good to go. Okay, so the next thing I want to do is I want to practice removing from the front of a doubly linked list. So let's talk about how that's going to work. Again, we're going to start with let's look at this 3-node list here for now. And then we're going to remove from the front. So what I need to do is I need to take first and just move it over. So no longer will first reference this node, first is going to reference the second node. But the problem though is that I still got references. As long as I've still got references to things, I'm going to have, it's still going to be in my list. So I need to sever this tie right here. And I do that by just changing previous to reference null. Now at this moment, there is still this node here has a next pointing to it, but that's okay. Remember, to be deleted, it's not that the node is not pointing to anything, it's that nothing is pointing to it. And notice nothing is pointing to that old first node, so it's gone. We do want to return the data that was there, though. We always like to do that when we remove. So we will get a variable of the data, and then we will deleted. So those are that's the key feature right there. Moving first over and removing that. Don't forget to return the data. Now, you may want to think about, though, what happens if the list is empty. Well, if the list is empty, we should really just throw a no such element exception. Would probably be the easiest thing to do. We could also just return null to indicate that they didn't remove anything, or in this case, return. Well, now see, we're dealing with int, so we can't return null. So we need to throw an exception for sure. What about if there's only one element in the list, though? Well, if there's only one element in the list, when we set first to first.next, we're really setting first to a null, which is, well, actually what we would want, because we're removing that item. But here's the problem. When we do that, then when we try and set first.previous to null, we've got a null pointer exception. So I need you to consider what happens when the list has no elements and when it has one element. So just be aware of that. Take care of those two special cases, and then use this diagram to help you do the third. Pause the video and give it your best shot. All right, let's take a look. We are going to return an int here. We're going to remove from the front, right? And so the first thing I'm going to do is I'm going to get the data that was there. So I'll just grab my first dot data, just like that. Next thing I'm going to do is I'm going to do, I can't do this because what if the list was empty? We need to check that first. So let's make sure. So if size is equal to 0, this is a foolish thing to do. So we're going to throw a new no such element exception. All right. Else, if the size is equal to 1, we need to do something a little bit different. So I'll say int data equals first dot data. And then I'll say first equals null, last equals null, because it's gone. We just want to set them back to their null case, and then I'll return the data. Else, I'll make another variable data here because I'm in a different branch of the if statement. It's okay for me to use the same variable name. So I have int data equals first dot data, and then what I need to do is say first is going to point the first dot next, which is totally safe because we know that we have at least 2 elements in our 2 nodes in our linked list. And then what I need to do now is say that first dot previous gets set to null, so it no longer references what would, because now first is at the second node, and I'm severing this connection right here to the previous node, our old first data, and then I will return that data. Okay. I guess we got to import that. I never remember which one that is. Import, so it must be in util. Java.util.no such element exception. All right, looks good to me now. All right. Okay, so what I want you to do now is I want you to write remove from the back. So we just did remove from front. Please do remove from back. All right, let's see how we did. Public int remove from back. So it's basically the same procedure, right? If the size is 0, let's throw an exception. And we could also say something. We could pass a string into the constructor of this exception. We could say, size of 0, something like that. Else, if the size is 1, we got to handle that special case as well. Double equal sign. So I do want to return the data. The size is 1. We'll use last, though, just so that it makes sense when you read it. But if the size is 1, first and last are the same. First will be set to null. Last gets set to null. And everything is gone. So then we'll return the data. Okay. And then our last case, of course, being that we have multiple things. Again, I'll make another data to hold that so I can return it. And I'm going to say last equals last dot previous. So last is going to be set to the value of the previous one. And now I got to sever the next connection because that last node is not supposed to be there anymore. And there we have it. Okay, what's next on our list? We are plowing through here, aren't we? All right. Now we got to remove a target node. So we're moving from the interior. This, unfortunately, is still going to be ON. We have not come across a data structure in this class yet where you can remove quickly from the interior of the list. So this is the shortcoming of array list. It's definitely a shortcoming of linked list as well. So let's take a look at this little picture I have here of 3 nodes. We're going to assume that the list is bigger than that though. So my previous is pointing to some other nodes I don't care about, and then this next here is pointing to some later nodes, but I really want to look at this. So we're going to have to iterate down our list. We're going to start with current at first, and there's nothing I can do to avoid that, right? I've got to iterate through until I find it. And I'm going to, let's assume that the target is somewhere in the interior, not the first, not the last, okay? So I'm going to connect when I find it, okay? When I find that target node, I need to somehow delete it. So I've got this pointer that's currently pointing right here, and I usually call it current as I iterate. Now, if current.next is equal to the data I'm trying to remove, okay? And this could be an index if we're counting by removing an index, but right now let's just remove a target value. This is one of the problems with using primitives, because if they give me if they say remove and they give me a primitive, normally that would actually mean to remove at that index. If they give you an object and you're looking for, like integer as an object, and you're looking to remove that data value. So for us, we're just going to remove a target value right now. It's similar to removing an edit index. All right, so once I know that I found a node where its next is pointing to the target I want to remove, I'm going to take its next and I'm going to bypass it. I'm going to jump across it, okay? All right, then once I do that, now current.next is this becomes current.next, right? So this is my new current.next. Once I've done that, I need current.next.previous to also bypass. So I'm going to take it over here. So I kind of want to do it in that order, and then that's all. Again, we need to consider some special cases and things like that. What happens if you try and delete an element that's not in the list? At that situation, you would just not do anything at all. We could make it to where we return the value. We could also just say return a Boolean. And in fact, I think that's what I would like us to do. So let's make it like that. Let's do public Boolean remove. Let's call it remove value, and we'll say like int val. So that's what I want to do. So we don't really need to return the value to the user, since they're the one that gave it to us. They already know what it is. When you remove from the front or back, oftentimes you're in a algorithm where you don't know what's at the front or back of the list until you remove from it. But if we're removing a specific value from the list, we clearly don't need it returned to us. We already know it. I just want to have a Boolean that tells me that it was successfully removed. So we'll return false if we don't find it. All right. Think of all your special cases, give it your best shot. This one's kind of tough, but I know you can do it, or at least get close to it. Pause the video and we'll talk about it. All right, let's give it a try. All right, so we are trying to remove here a specific value, and we need to iterate through this, okay? I'm going to go ahead, though, before I iterate, I think I'm going to look at just a couple of situations first. So, no, that's okay. I don't need to do that, actually. So I'm going to say node current is equal to first. So I've created a new node that is equal to first. And what if the very first node is our target node? Well, let's take a look. If first.val dot data is equal to the value that we're trying to delete, well, I already have that method. It's called remove. Is it remove at front or remove from front? So we'll just call that method remove from front. Does that make sense? All right, what about if we have to remove from the back? Well, I'll say else if last.data is equal to the value, then I will say remove from back. And we've already taken care to handle the special situations in each one of those. So that should be good. All right. Well, there is an issue here, actually, that I'm thinking about it, because what if the list were empty? If the list were empty, then you can't remove anything. So I'm going to do that first. If size is equal to 0, we'll just return false. And I actually realized that when we removed from the front and back, we did not decrement size. We need to do that. So make sure that you've done that. All right. That'll take care of it. So those will decrease in size there. All right, else. Now we have to handle what's on the interior. This is where we're going to start moving things around. So I'll say while current dot next does not equal null. All right, so while current dot next does not equal null, if we get that far, then we'll just return false because we obviously were not able to delete it. Say if current dot next is equal to the value that we're trying to remove. Ooh, current.next.data. If current.next.data, so that's me asking if the target value is the current node dot next data, right? So current.next data. If that is equal to the value, then we found what we need. So we will say current.next equals current.next.next. Remember, current.next is not null, so this is safe. Now that I've done that, current.next is already moved over. So now I can say current.next.previous needs to point to current. And we have effectively removed that value. We will decrease the size and we will return true. We also need to do that here. Return true. And we need to say that here as well, because we promised to tell you if it actually got removed. All right. So what do we do if current.next.data does not equal the value? Well, then we iterate forward. So we say current becomes current.next. What do we do if we get through the whole thing and we never found it? We return false. Okay, so that should be everything that we need. Let's test it. Make sure you included those size decrements that I forgot earlier. And let's run it. I'll make a new doubly linked list. Okay. And let's try some adding. We'll add like a 9. We'll add a 15. We'll add a 24. All right, so let's inspect it. See if we can figure around. Those are two references to the first and last. We can start in either direction. Let's start with the first, and we can see that we have another node and another node. All right, I can go backwards by using the previous command until I get to null. So that's working pretty well. All right, we've done that. Let's add to. Let's see. We've been adding to the front, right? Let's add to the back 17. And just in case I forgot, let's add to the front 24. So let me inspect that, make sure. This should be 24, yep, and this should be, what was it, 19, 17. That's it. Cool. Might help if we made a 2-string while we tested this. That would probably have been smart, but I didn't, so we won't. All right, let's try remove from back. $17 has been removed, and now let's inspect that. It's been removed. Everything's looking pretty good. Let's remove a specific number. So let me inspect that again. All right. So I'll go. Oh no, I don't want to do that one. Let's go to the first. Let's see, next is a 9. Next is a 15. Next is a 24. So I'm going to remove. Let's remove the 9. See if that works. So we're going to remove the value 9. And it's removed. Now, if I try and call that again, it should return false, which it does. All right. Well, I'm going to leave you to finish off a couple more methods in this package here in this doubly linked list. But I hope you found that interesting. But as a final summary, I want to go over the changes now to our big O, and I went ahead and included array list as well, just so we can review that. So what happens if we inserted the front? Well, this is O1, right? Oh, I'm going to get tired handwriting all this. Let me do I'll just do that. That's smart, right? So that's going to be O1, and this is going to be inserting at the front of a array list means you got to push everything back, y'all. That's slow. You got to then move everything back. Removing at the front, that's O1 for us here. What about on the array list? Again, once you remove from the front, you got to pull every single data item. It's got to slide forward. That's slow. That's ON. Viewing the front, that's O1 because we can, and we haven't written just the get front yet, but you will be writing that yourself. But I think you can imagine that's O1. But that's going to be O1 as well for the array list, since the array list has instant access to any index. We're going to insert at the back at O1 in our doubly linked list, but the array list is also O1. Remember, inserting at the back of an array list, adding to the back of it is very easy for an expandable array because you don't have to slide anything up or down. We've now made it, these are new for us. This used to be ON when we were singly linked. Now we're doubly linked, and it makes it a lot better. All right, let's think now. We're moving from the back, though, of a array list. Again, you're just going to remove the back element and decrease size is basically all you do. So that's nothing. Viewing the back is O1 because we have a reference to the back for a list, and of course, viewing any index in an array list is O1. All right, removing a specific data item is going to be ON, unfortunately, for both of them. And viewing a specific index, unfortunately, is ON. So if we want to access a certain node, we got to loop through them. But for the array list, it's O1 because we have instant access to any one of those. So I think you can kind of see the comparison between the two. The array list really loses out still at the front, but that instant access to any index is a huge advantage of the array list. But the doubly linked list giving us access, constant or O1 access to both the front and the back is pretty sweet. Okay, so that's it for this video, and I'll see you in the next one.